Hello, my name is Anton Korikov, and this is joint work with Christopher Beck from the University of Toronto. I'll be presenting our paper, Counterfactual Explanations via Inverse Constraint Programming. Consider, for example, a delivery service scheduling some orders from a group of clients, and they use a discrete optimization algorithm such as MIP or CP. After producing their schedule, one of their clients asks, why did we not receive order A on Monday and order B on Tuesday? We aim to address such questions through the framework of counterfactual explanations. Our paper is in part motivated by the GDPR, and in the GDPR there's a strong emphasis on the need for explanations for users subjected to decisions. So this is our primary focus, but we also think our approach could be beneficial to other people in the system, such as the decision makers, for example, the delivery service from our previous example. So one of the approaches that has been championed as user-centric is that of counterfactual explanations, and part of the reason for that is because it requires no algorithmic knowledge on the part of the user. So we start with some inputs A, which are fed through a decision algorithm, and have a decision X star. The explanation begins with a contrastive question from the user. They ask, why decision X star, and not some alternative decision Xi? We call this alternative decision Xi a foil. This is a hypothetical decision defined by the user. And the explanation then is equivalent to finding the inputs B that would have resulted in this alternative decision Xi being reached. Typically, we want to find some sort of minimally modified B relative to A. And so both the inputs B and the decision Xi are counterfactuals. They're contrary to the facts in this case being the inputs A and the decision X star. This is why this is called the counterfactual explanation. Alternatively, a user might be interested in a set of hypothetical decisions. They might ask, why X star and not a decision in some set Xi? And in this case, we would call the set Xi the foil set. So counterfactual explanations have attracted a considerable amount of attention in machine learning and more recently in model-based AI systems such as AI planning. And so we aim to build off of one of our recent works where we extended the framework of counterfactual explanations to optimization systems. And so specifically, we formulated an explanation in terms of the changes to the cost coefficients of the optimization problem. So let's consider an example. Let's return to our users ordering parts for delivery. Each order has some order priority. For example, part A might be express shipping and a priority level 5, and part B might be standard shipping and a priority level 3. The delivery company then minimizes the priority-weighted delivery times and produces some optimal schedule X star. Upon seeing part of the schedule, a client asks, why did we not receive order A on Monday and order B on Tuesday? And we define the foil set as the set of solutions that satisfy these delivery times. Then we present the user with an explanation in the form of the counterfactual order priorities that would have been required for one of these solutions in the foil set to become optimal. So the form of the explanation is the minimal change to the objective parameters of the problem. Now we consider these types of explanations for standard constraint optimization problems, where we have some decision variables x, part of a feasible set x, some objective parameters c, and an objective function f. And the problem is to find an optimal x star that minimizes the objective function. Our definition of an explanation was inspired by inverse optimization, where we're given a known solution xd, and the goal is to minimally change the objective parameters such that this known solution becomes optimal. So we'll call the modified objective parameters d and control any requirements on them with the feasible set c, and use some norm, typically L1, to measure the distance between the modified objective parameters d and the initial objective parameters c. We'll minimize this norm with the constraint that the known solution xd needs to become optimal. So this is the form that inverse optimization is typically studied in. You can notice that the constraint parameters are not allowed to change. And so as far as we're aware, for inverse combinatorial optimization, there's no general approaches to dealing with cases where the constraint parameters change. And so since one of our ideas is to work with inverse optimization algorithms for explanations, we also decide to, for the moment, focus on changes to the objective parameters and not to any constraint parameters. So now we can see that if we generalize inverse optimization to deal with a set of alternative solutions as opposed to a single alternative solution, then we can create a natural definition for these types of counterfactual explanations. So if we're given a forward problem CFX and some decision algorithm leading to an optimal decision X star, and if we can express the hypothetical alternative solutions from the user with a set of constraints, then we'll call these constraints the FOIL constraints, and together with the initial constraints in the problem, these will define our FOIL set Xi. And so the question again is, why X star and not a solution in Xi? And then we'll define the nearest counterfactual explanation problem as the problem of finding the minimal change to the objective parameters such that a solution from the FOIL set becomes optimal. So this definition is very similar to that of inverse optimization. It's identical except for the fact that we're not dealing with a single solution anymore, but we're dealing with a set of solutions that we want to make contain an optimal one. And so this generalization creates a more complicated problem, and as far as we're aware, we don't know of any general methods for dealing with such problems yet. So to make progress, what we do is we define a special type of explanation, which we think encompasses a set of useful explanations nonetheless, that has a special structure that allows us to use inverse optimization techniques. And so in this paper, we prove that for a subset of NCEs, a single FOIL always remains optimal. And what we mean by this is that it remains optimal for all feasible alternative objective vectors. This means we can solve these problems in two steps, first by finding this optimal FOIL, and then by using inverse optimization with this FOIL as the known solution. We then introduce CP into the inverse optimization algorithms and demonstrate the effectiveness of an early stopping criteria for CP. And then we show that a CP-MIP hybrid can be effective in the inverse optimization step when the forward problem or the initial problem is well suited for CP. So up to now we've been quite general with our definitions, but from now on we'll be considering discrete optimization systems with a linear objective, and we'll be measuring the distance between two objective vectors with an L1 norm. So now let's define the special type of explanation problem we've been talking about, and we'll call this a partial assignment nearest counterfactual explanation. We'll start with an example and go back to our clients placing orders with each order having some objective priority. Our first requirement is that in their contrastive question, the users specify a set of partial assignments. So for example, if the x's are delivery times, this might look something like xa equals Monday and xb equals Tuesday. Now we could present the user with the minimal change across all the order priorities as our explanation, but in the general case, this might not be very useful. Especially if there's other clients in the system, then there might be many orders of which our user has no knowledge or no control over. Additionally, it might be important to protect the privacy of those other users. Alternatively, perhaps our user is just interested in isolating some variables for their explanation. And so instead of presenting the user with the minimal change across all of the order priorities, we'll instead include in our explanation only the priorities associated with the variables that the user included in their question. So in this case, variables A and B. And so we'll use the set M to denote the variables that were included in the FOIL constraints and the corresponding objective parameters. And for those variables that are not in this set, we will require that their corresponding objective parameters remain at their initial values for the explanation. And so for the general case of a partial assignment NCE, if we look at the decision variables and the objective parameters, our user asks the contrastive question, why not satisfy the partial assignment XP? So our first requirement is that in the PA-NCE, the user constraint set be a set of partial assignments defined over the set M, fixing these variables to their specific values. And our second requirement is that for the objective parameters that aren't associated with the variables in M, these need to remain at their initial values throughout the explanation. So now we can show that for any PA-NCE, there is a FOIL which is optimal for any feasible parameter vector. So let's consider some of these FOILs. Recall that we have a linear objective, which we can split into two components. So first we have the components where the variables are in M, and these variables in the FOIL constraints have been assigned to values. Since all the FOILs satisfy the FOIL constraints, the contribution from this component is equal for all FOILs. Then we have the component where the variables haven't been assigned, but the objective parameters in this component are not allowed to be used in an explanation and must remain at their initial values. And so as the objective parameter changes, the only change that occurs to the objective function is due to the first component, but across all foils, this is an equal contribution. So this means that any foil that was optimal at the initial objective parameters is going to remain optimal for any modified objective parameter vector. And so this means we can solve a PA in CE in two steps. First, by finding this optimal foil, and this is simple to do. All we have to do is add the partial assignment constraints to the initial problem and solve. And then by using inverse optimization with this foil as the known solution. So now we need a bit more background on how inverse optimization problems are typically solved. The state-of-the-art is a cutting plane algorithm defined for inverse MIP by Wang from 2009. We split the inverse problem into a subproblem and a master problem. In the master problem, we have a set of known solutions S0, and the goal is to minimally change the objective vector such that xd is no worse than any of these known solutions in S0. Once such a vector has been found, we pass it to the subproblem, and the subproblem is identical to the initial forward problem that we're trying to modify, except that it uses this new objective vector d1. The goal of the subproblem is to try to find better solutions than xd given this new parameter vector. If we find such a solution, then we pass it back to the master problem and add it to the set S0. This creates a cut and makes the previous solution infeasible. We continue looking for new objective vectors in the master problem and passing them to the subproblem. And we know we're finished if in the subproblem xd is optimal at the current objective vector. So the form of the master problem is to minimize the change in objective vectors, and we have a linear constraint for each of the known solutions in S0, requiring that xd be no worse than this solution. So in the past, both of these problems have been defined with MIP, but there's nothing stopping us from defining them with CP. And so if we do this, this gives us what we call inverse CP. Alternatively, we can define one of the problems with MIP and the other with CP, and this would give us two MIP-CP hybrids. And so what we show in our results is that if we use a hybrid where we use MIP for the master problem and CP for the subproblem, then for the cases where CP does well in the initial problem that we're trying to explain, then this hybrid has good performance. And this isn't too surprising because the master problem has a relatively simple linear structure which is well suited for MIP, and the subproblem is very similar to the initial problem, differing only by the objective vector. So if CP does well for the initial problem, it will likely continue doing well in the subproblem. So in addition to these three new algorithms, we also define an early stopping criteria, which we show has benefits when CP is used in the subproblem. So the master problem provides new objective vectors for the subproblem. And in the initial algorithm, the subproblem is solved to optimality every time. The optimal solution is added to the set S0 in the master problem, where it forms a cut, because at this objective vector di, xd is no longer optimal. However, any solution that is better than xd at this objective vector would also be a valid alternative cut. And so what we propose is that once such a valid cut has been found, that we limit the amount of time spent in the subproblem looking for a better solution. So if we look at a graph of solution quality versus time in the subproblem, it might look something like this. And so once we've found a solution that's better than xd at the given objective vector, we can define an early stopping criteria and return the best known solution up to this point without necessarily solving the subproblem to optimality every time. So now we've defined our problem and our algorithms. For our experiment, we simulated the explanation process for two forward problems. First, the 0-1 knapsack and single machine scheduling with release dates. For each of these, we simulated a user asking a contrastive question by generating a set of partial assignment constraints. This gave us our partial assignment, nearest counterfactual explanation instances. And we solved these first by finding the optimal foil, and then with inverse optimization. To find the optimal foil, we used either CP or MIP, and for inverse optimization, we used our cutting plane algorithms. Specifically, we had inverse MIP and inverse CP, and two inverse MIP-CP hybrids depending on whether CP was used in the master problem or the subproblem. And we also tested our early stopping criteria for 2 of these. The results were dominated by the second stage, that is the inverse stage, and this is because it involved multiple iterations of the subproblem, and each iteration of the subproblem was of comparable difficulty to the first stage of finding the optimal foil. So for the 0-1 knapsack, the best performance was achieved with an inverse pure MIP algorithm. This wasn't too surprising because knapsack is typically very well suited for MIP solving. Now for single machine scheduling, we got the best performance out of a MIP-CP hybrid where CP was used in the subproblem. And this was due to the strong performance of CP for the initial scheduling problem. So the takeaway here is that when CP does well for the initial forward problem, then it is also beneficial in the subproblem of the inverse cutting plane algorithm. And that is because that subproblem is very similar to the initial problem, differing only in its objective vector. Next, we look at the effect of the early stopping criteria and see that it's beneficial when CP is used in the subproblem and the instance size is large enough. On the other hand, it has practically no effect on when MIP is used in the subproblem. And so we speculate that one of the reasons this might be the case is that CP could often be finding the optimal solution, but then taking a long time to prove that it's optimal. And so the early stopping criteria would stop us from waiting for CP to prove optimality when we don't need to. And this effect might not be as large for MIP. Finally, when CP was used in the master problem, the performance was quite poor. This wasn't too surprising because the master problem is a relatively simple linear formulation which is well suited for MIP. However, if in the future we wish to define the counterfactual explanations with more expressive constraints and objectives, then CP in the master problem could be a useful way of doing this. In conclusion, we defined a subset of nearest counterfactual explanation problems where one foil always remains optimal for all feasible counterfactual explanations. And we solved these problems first by finding that optimal foil and then by using inverse optimization. To do this, we introduced inverse CP both in a pure CP and a hybrid MIP-CP form, and we showed that an early stopping criteria can be beneficial when CP is used in the subproblem. And finally, we showed that a MIP-CP hybrid, where the MIP is used for the master problem and the CP is used for the subproblem, can be effective when the initial problem has good CP performance. So to use our solution method, we required a special structure, and we defined this structure in terms of the form that the user constraints needed to take, and with some restrictions on the explanation parameters. The most ambitious next step would be to try to solve the general nearest counterfactual explanation problem, which, if you recall, is a generalization of inverse optimization dealing with a set of alternative solutions instead of a single alternative solution. And we would also be interested in looking for other explanation problems with special structures that might have their own solution methodologies. Thank you for listening to our presentation, and I'm happy to take some questions.